Hello everyone, this is Jiashun Wang. Today I'm going to present our work on multi-person 3D motion prediction with multi-range transformers. First, let me briefly introduce the background. 3D human motion prediction has drawn great attention these years. This task is about predicting future motion sequences, given a sequence of history, and most studies are focusing on single-person motion. And these studies usually neglect the movement of the root joint, which means they always center all the poses at the origin. While multi-person motion prediction is relatively underexplored and more challenging. First, we need to consider modeling the multi-person interaction. And another problem is we need to model pose and trajectory jointly. For example, if a man is running and catching another person, the pose he does is related to whether he catches up with another person or not. So in this case, pose and trajectory should be considered jointly. This task is given a scene with n persons and their corresponding history motion. We aim to predict their future 3D motion. Specifically, given big X n 1 to k representing the history motion of person n, where n could be 1 to big N and k is the time step. We aim to predict the future motion xn k plus 1 to t. We use a vector xnk containing the Cartesian coordinates of all the J skeleton joints to represent the pose of the person n at time k. We propose our multi-range transformers to solve this problem. So let's say this is a scene with 3 persons, and we use green color to represent the history sequence. Firstly, we take predicting this person 1's future motion as an example. The blue color represents the output future motion. For this individual motion, we use an offset to represent the sequence, because this is more beneficial for predicting smoother results. While for modeling the whole scene, we just use the original xi because this is more beneficial for modeling the interaction in the 3D space. And for the output, we also use the offset representation. This leads to smoother outputs. We use a local range transformer encoder focusing on the individual motion to generate smooth and natural prediction. We use a global range transformer encoder to perform self-attention across different persons and different time steps. This is for modeling the global interaction. And we use only a single pose as the query for the decoder instead of a sequence of motion. This could create a bottleneck to force the transformer to learn to predict the future, instead of repeating the existing motion. On the right, we show the architecture of the transformer decoder. The encoder architecture is similar with the decoder, except that the query key and value are from the same input. Next, I will introduce another 2 techniques we used in the paper. First is the discrete cosine transformation (DCT) and inverse DCT. DCT is beneficial for modeling human motion based on its energy compaction property, and it nicely captures the smoothness of human motion, particularly in terms of the 3D coordinates. Here we explain the reason we use 3D coordinates as the representation. The first reason is that a lot of multi-person motion data are obtained by pose estimation techniques, with only 3D joint positions available. And the second reason is that we think the 3D joint positions are beneficial for modeling the interaction between persons. The second is the spatial positional encoding proposed by us. SPE encodes the spatial distance between the query token and the tokens of every time step of each person, and it is very helpful, especially in a scene with a crowd of persons. So now, we may have a question, why local range and global range? Specifically for local range encoder, the task of synthesizing a natural motion based on previous states itself is actually a challenging task. To ensure the smoothness of the motion, the model requires dense sampling of the input sequence. For global range encoder, we consider the interaction of all the persons in the whole scene. To help the model to focus on the interaction instead of the motion, sparse sampling of the sequences are used as inputs. Of course, with infinite compute bandwidth and data, one big transformer could be enough to encode everything. However, realistically, with limited compute and especially restriction from the scale of dataset, we find a separate process of different aspects of data largely reduces the optimization difficulty. We also propose a novel training strategy which is progressively increasing the input sequence length to the model during the training and inference. since the transformer could handle variable length data. The advantage of such design is that when predicting longer motions, we still maintain the early motions as inputs to the model. It is a very helpful strategy to reduce the error accumulation. During training, we can provide x1 to k to predict xk plus 1 to 2k, xk as the query. Or we can provide x1 to 2k to predict x2k plus 1 to 3k, and x2k as the query, and so on. During the inference, we can predict the future motion in an autoregressive way. Given x1 to k, our model predicts xk plus 1 to 2k. Then, given the input and our prediction results, we use them as inputs to predict x2k plus 1 to 3k, and so on. For the data we use, we have two settings. The first one is scene with a small number of persons, and the second setting is a scene with large number of persons. We try to mix the current dataset to generate this kind of data. For unifying all the data, we pre-process the data by picking a subset of joints that is common to all the datasets and scale them to the similar height. For scene with more persons, we randomly put them into a square plane ground. For the qualitative results, first we show some examples of our multi-person 3D motion prediction results. Then we compare our method with the other methods on different datasets. It can be seen LTD is affected by the pulse positions. And here HRI is also affected by the pulse positions. And this is why we do not use a sequence but a single pulse as the query. Social pole is just predicting freezing motions. Here is another example, and here LTD fails to predict the correct walking motions. And HRI predicts freezing motions quickly. Social pole predicts freezing motions quickly. We report the MPJPE in 0.1 meters of 1 second, 2 seconds, and 3 seconds predicted motion on CMU mocap, MPOS3D, 3DPW Mix1 and Mix2 respectively. In both cases, with a small number and a large number of people, our method achieves state-of-the-art performance for different prediction timelines. We achieve up to 20% improvement when compared to previous single-person based methods, and achieve up to 30% improvement compared to the multi-person based methods. For user study, we report the average and the standard error of the score. A higher score means users think that the results are more natural looking, and a lower standard error indicates that the scores are more stable. Our results get better reviews consistently across all the datasets. And we also show the distribution of the moving distance between the start and the end of the prediction. It shows that the other methods intend to predict a motion with less movement. We observe the results of other methods sometimes just stay in the same spatial location, while the ground truth is moving with a large distance. Our result is very similar to the ground truth. Thanks for watching.